So what is the fundamental reason why we are unable to get power amplification using an LTI network, even though we have a additional power source? The main reason we are unable to get power amplification at this output terminal V2, power amplification of the sinusoidal source of V in, right, of the sinusoidal source. So we are unable to get a power amplification at V2 simply because what an LTI system does is LTI system simply pushes the sinusoid up by some DC term, right? It doesn't really increase the amplitude of the sinusoid, right? So ultimately what we want, and if you have an LTI system, in case of an LTI system, in the absence of VDC, if this were my output, right? So this were my output without VDC, in the presence of VDC, this output essentially becomes something like this, right? So this is with VDC. So the peak to peak amplitude, the amplitude of the sinusoid, or the peak to peak voltage doesn't really change. Hence the power of the signal at the output doesn't really change, regardless of the fact that you have one extra DC supply, or you might have a bunch of extra DC supplies, right? So what are we after? We are after a network which can increase the amplitude of the sinusoid itself, okay, not only just shift the sinusoid by a certain amount, right? So in essence, what we are after is the fact that this term, whatever this term, this alpha times Vp, should get multiplied with something so that the amplitude of the sinusoid at the output itself increases. Now, why is another way of thinking about this problem is the fact that this LTI system is not able to transfer the power of the DC signal, of the DC source, to a frequency of omega naught, right? So this signal, this source Vi, is acting at a frequency omega naught. And what is the frequency of the DC source? What is the frequency of a DC source? The frequency of a DC source is 0. So in other words, what we are expecting the transference of the power from 0 frequency to a non-zero frequency omega naught. If that happens, then it is possible to expect that the amplitude of the sinusoid will increase. If that doesn't happen, then naturally the amplitude of the sinusoid cannot increase. And as we know from our basics of LTI system, right, from basic circuit theory courses, we know that an LTI system does not cause any shift in frequency of a signal. Since an LTI system does not cause any shift in frequency of a signal, no power from this DC source can be delivered to a frequency of omega naught. Okay, so what is the solution then? The solution is, you cannot use an LTI network. If you have an LTI network, you will not get any transference of power from your DC source to any port or across any load that you want. Okay. So what happens if this network is not LTI? Let's say this network is non-linear, right? So what happens if this network is non-linear? Let's say this network now is non-linear. Is it possible? The question we are asking is it possible now for transference of the DC power to a frequency of omega naught? Let's see. Let's say this is VDC again, this is V in, this is RS, this is RL. Let's say V in is Vp sine omega naught t. And note that this is a non-linear network. Since this is a non-linear network, we cannot use superposition. Unfortunately, we cannot use superposition, which means we'll have to take the effect of both the sources into account simultaneously. Now, a generalized solution for any nonlinear network is not possible. So what we will say is that let's again take an approximation and say that let's assume this nonlinearity is a polynomial type of nonlinearity, right? By that what I mean is, if this is my port V2, this V1, so if this is my port V2, let's say the output voltage V2 is related to the sources V in and VDC as follows. Let's say let V2 be equal to A1 times V in plus B1 times VDC plus A2 times V in plus B2 times VDC whole squared plus let's say is A3 V in plus B3 VDC whole cube and so on, right? So let's say this is a generic polynomial type of nonlinearity. The values of A1, B1, A2, B2, A3, B3 and so on and so forth can be dependent on the type of nonlinearity that we have within the box. Okay, so this was essentially an expansion of V2, right? So this was V2, not the power. Power is obviously average of V2 squared over R, right? So V2 will be equal to A1 Vp sine omega naught t plus B1 VDC plus A2 Vp squared sine squared omega naught t plus B2 squared VDC squared plus 2A2 B2 VDC times Vp sine omega naught t and plus so on, right? So I am for the purpose of brevity, I am ignoring the higher order terms, right? It will just help make the point by making the algebra simpler. Okay, so let me ignore the higher order terms. If I do that, what do I end up with? Let me collect all the similar terms together. So what do I get? What are the terms for sine omega t? The first term here, and I have this term here. So I get A1 plus 2A2 B2 BTC BP sine omega naught t plus there will be a DC term, and the DC term will be this B1 VDC plus this square VDC squared plus there will be once we expand this, sine squared omega naught t will be half of, right, will be half of a2 bp squared, right, and you will have another sine 2 omega naught t, right. So you will have another term called this plus some constant times cosine 2 omega naught t, right. Okay, so now if we stare at this term, if we stare at these terms, what do we see? We see that there is this nice term over here which is proportional to sine omega naught t, but it is appended with a1 plus a2 b2 vdc. Now interesting thing is that vdc makes an appearance in the amplitude of sine omega naught t, right. vdc makes an appearance in the amplitude of sine omega naught t, which means that now if you have a nonlinear system, it is possible to increase the amplitude of the sinusoid because of this cross multiplication that is happening because of the presence of nonlinearity, and hence it is possible to increase the amplitude of the sinusoid. In other words, we can also say that it is possible to transfer the power from the DC source to from zero frequency to omega naught. Okay, so what are the other terms? The other terms, this is a DC. This term that we see here is DC, right? So this is the DC, and this is a, and this last term here is a cosinusoid at twice the frequency, right? So your output now, right? Your output now, what will the output look like? Under these conditions, your output will look like you have a DC term, right? You have a DC term. So let's say this is the DC level. What do you have else? What else do you have? You have a sinusoid. More importantly, you have a sinusoid whose amplitude is a1 plus 2a2 b2 times vdc, right? That vdc factor is important. So essentially you have a sinusoid whose amplitude is how much? a1 plus 2a2 b2 vdc, 2a2 b2 vdc times vp. It was vp initially, but now it becomes a1 plus a2 plus 2v2 vdc, and you have another term, another cosinusoid signal, right? So you have another cosinusoid signal of double the frequency, right? So essentially you have another cosinusoid signal. Excuse me, I didn't sketch it properly, so all these terms I am sketching individually. So the sinusoid should have been at a zero mean, right? Once we add them up, then we can shift them together. So this was the DC, and the cosinusoid will be something like, right? So what are the consequences of nonlinearity? The consequences of nonlinearity are it's possible to transfer power from DC to omega naught, thereby increasing the amplitude of the sinusoid across RL, right? Thereby getting more and more power. And second, another unintended consequence is can give rise additional frequency components. At harmonics of omega naught, right? So this frequency is at 2 omega naught. The intended frequency is at omega naught. We are able to get an amplification of the intended frequency, but at the cost of introducing an unintended frequency component also, right? So a nonlinearity is good and is bad in some ways, right? So there are many things in life which are good in small doses but not so good when you keep repeating it in larger and larger doses. This is one such example. You cannot do away with nonlinearity. We need nonlinearity to get power amplification. However, along with it also comes a small or negligible or non-negligible, it depends, signals. Along with the power amplification, we get signals of different other frequencies which we don't want, right? We don't want signals as 2 omega naught when we have provided a signal at omega naught. Okay.